Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is rotating oranges. Let's go to LeetCode and give this problem a read. You are given an M cross N grid where each cell can have one of the following values. 0 representing an empty cell, 1 representing a fresh orange, 2 representing a rotten orange. Now every minute, any fresh orange that is 4 directionally adjacent to a rotten orange, which is represented by 2, becomes rotten. Okay, return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is not possible, then return -1. Well, why is it not possible? Maybe some oranges are not basically in touch with, or maybe not 4 directionally adjacent to any rotten orange. Then there is there is a gap. That means you cannot, those fresh oranges are not in touch with rotten oranges, so they cannot get rotten. Now let's see how we're going to do it. This is a BFS problem. We have already done similar problem, which is walls and gates. Please check it out. I've already done that. It should be on our channel. Okay, let's do this problem. So we have 3 kinds of cells. One is one has 0 is basically empty cell. Then we have 1 means fresh orange. Okay, yeah, fresh orange. Then we have 2 is rotten orange. Okay, so we need to basically return the minimum number of minutes that it will take all the oranges to get either bad, rotten, or there is a situation where like it doesn't spread anymore. There are no more oranges that can get rotten because there is a gap, like they're not in touch with the rotten oranges, those fresh oranges. So now you can see right here, they have shown in this example that this is the first state. Right, this is the first state where only one of the orange is rotten. This is the one that's rotten. Then in the next minute, it's a 0 minute. Then at the 1 minute, what happens is these two oranges were in touch with this rotten orange. So this one and this one. So in the next state, what happens? These two are now rotten. So this is rotten, this is rotten, and this is rotten. Now what happens in the minute 2? In the minute 2, what will happen is we're gonna see what are the oranges that are in touch with these rotten oranges. Well, this one there is nothing in touch with, but this one is, and this one is. So that's why these two have now also become rotten. Okay, now what happens in minute 3? The orange that was touching with this rotten orange, this also becomes rotten. So this also gets rotten. So now we have like this, and this rotten, and then there is one more remaining orange which will get rotten because it's in touch with this particular rotten orange. So this will also get rotten. So our answer would be 4. So how are we actually going over these rotten oranges and then trying to find what are the oranges that are in touch with these rotten oranges, and what are the fresh oranges that are in touch with this rotten orange, and then basically add those two queues so that we can process them. So we can solve this as BFS, DFS both, but the best solution would be using a BFS, so that at the same time you can see all your neighbors, all the neighboring cells which are fresh oranges, not empty, not out of bound, fresh oranges, and then we just pick those and basically append that to our queue. And now at this point we are considering them as rotten also, so that they can infect the other oranges. So okay, how are we going to approach this problem? So basically, as I said, like it's same as gates and walls. So what will happen is we'll have a queue. So initially we'll have all the rows and column calculated and visit set. Then what we are going to do, we're going to have this queue, and we will iterate over our grid and collect all the rotten oranges addresses. So this one will be 0 1 2 0 1 2. So initially only one orange is rotten. There might be more oranges that are rotten. That's why we are using BFS, so that we can put those into my queue, and then one by one I'm processing each rotten and their neighbors and see which neighbors are fresh oranges, pick those because they have to get rotten, and then append them to the queue so that I can process them further in time, basically at the next minute. So I will append, basically in this case, 0 and 0. That's the only rotten orange right now. Then at the same time, while I'm like going over the grid, I will also calculate the total number of oranges. Total oranges in this case is 1 2 3 4 5 6 7. 7 is total number of oranges. The reason I am basically calculating that, so that later I can basically once I'm done iterating, there are no more changes being made, like there is nothing in my queue that I can process. So what will happen is, like, then when I'm returning this time, what if there are other remaining fresh oranges? I will have to compare it with if my complete visit set, which will have all the rotten oranges, is equal to total oranges. If it is not, I will return -1. Otherwise, I will return the number of basically just the grid. I will return, oh sorry, time, not the grid. This time we are returning the time. Last time in walls and gates we were returning the grid, but this time we will be returning the time. So initially the time is 0. At 0 minute there is only one orange that is rotten. So what will happen? We will have our loop while q. Now this small q, we will take all the elements of q. Q becomes empty now, so that we can process the oranges, the fresh oranges that will be processed on the next, or rotten oranges which were fresh and now we are like basically they become rotten. We will push them into this queue so that they can be processed on the next minute, not this minute. This is time 0. So what will happen right now is I will have my for loop. So for I can call it like, let's say, orange, or maybe, you know, it's better to call it node. We're working with graph in queue. Okay, so I will process this particular node, then I will have the row and column from this node. Now what will happen is I want to basically calculate, to check all the neighbors of this, neighbors of R and C. So all the neighbors of R and C. So what I'll do is I will have, like, I can just say visit all the neighbors of visit all neighbors of this particular node, and if they have fresh orange. So fresh orange, that means what? That means they are valid, like it's equal to, basically it's these, we will be using directions to basically calculate the top, bottom, left and right, and whichever has one, those are the one we will be processing. Okay, and also given that they are in bound, and it's a fresh orange. So if it is a fresh orange, I will basically append that to my queue. Okay, append that to my queue. So append to my queue, big queue. Okay, append to my queue. This is an important step. And then once you come out of this for loop, you will be basically, if we have added something into our queue, then only we will increment our time by 1. Otherwise, and then finally we will return our time. And the reason I'm doing this is, what if in this particular case we do not add anything to my queue? Then I don't have to increment my time to basically you know, there is no minute that can get more oranges rotten. Okay, so then I don't have to add this time, because if I increment time, that next time will be visiting all the neighboring fresh oranges and basically making them bad. Okay, so this will be it. I think worst case time complexity would be time-complexity in this case would be big of n cross m. That is the total number of basically nodes we will be visiting. And then space complexity is also going to be big of m cross n. What if in the beginning everything was rotten? So we'll be pushing that to my visit set. And remember this here, right here, when I'm visiting, I will add that to my visit set, and I will also check that these neighbors I'm about to visit, they are not already in my visit set. All right, so that is it, guys. It was a simple BFS problem, and there will be tons and tons of problems that we'll be encountering that are going to use BFS just like this. So it's important that we, kind of like not memorize, but like we understand the flow of BFS on these kind of problems. So initially what we'll have is a row and column and visit set declared. So row will be the length of our grid, and then length of our grid 0. That is my column. Now visit is going to be basically the set to represent, like to basically collect all the nodes that we have already visited. So what do we want to do now? Also, as I said, we want to have a queue, so that this will be our queue. Queue is going to be empty in the beginning. Then we will have also total oranges. Initially it's 0. So now for row in range rows, and for C in range columns, if this grid at row and column, what I'm trying to do is I'm trying to find the rotten oranges right now. So if this is equals to 2 represents rotten oranges, then what I want to do is I want to append that to my queue. So queue dot append this R and C. Okay, at the same time, what I want to do is I also want to increment my number of oranges. And there is one more thing. If this grid is equals to 2, so I'll have just same thing right here. And if it is equal to 1, that means it's a fresh orange. Then also I will increment. So I will just remove this and just simply increment the orange number of oranges. That's it. Now what do? We are going to basically process our queue. That's what you do in BFS. So process all the rotten oranges and their neighbors. So while this big queue, then let's empty this big queue into a small queue and have this big queue as empty this, so that we can process the next level. Initially let's have our time as a 0. It's a 0 at time. Then we're going to have for node, or you can call it orange. I can call it orange. For orange in my queue, take out the row and column from this orange location. Now is what we are going to do is we're going to explore its neighbors. So let's have something called directions. Array is basically like, first time I'm basically incrementing the row. You will see why I'm doing this. Then -1 and 0, so I'm decrementing row. So that means going down and up, and now let's decrement and increment our basically column. So row is going to be 0, and then 1, and then for decrementing column we'll have 0 and -1. All right, now let's go over RBR and DC in directions, and new row, new column is what is going to be. We will add those values. So BR plus R and DC plus C. Those are my new neighbors. So every rotten orange has 4 neighbors, or maybe it's supposed to have 4 neighbors. Some might be out of bounds, some might be empty, some might be fresh orange. We only want to consider fresh oranges. So how do you consider fresh oranges? Fresh oranges? So I would say, first of all, this has to be they have to be in the bound. So what usually our scenario is basically new R is basically if this is greater than 0, or maybe like discard the ones that are out of bounds, or those are equal to 2 or equal to 0, like empty. So if this is new R is less than 0, or new column is less than 0, or new r is equals to row out of bounds, new column is equals to c, okay, or this new r and c, it's in visit already been visited, so it's in new r comma new c, it's in visit set. That means it has already been visited. It's either a rotten or already processed rotten node. So if this is in visit, or there is one more thing, if this is equal to 0 or 1, so maybe we can say just like it's equal to grid is new r, new c is not equal to 1, because that's what I want to process. All right. So I hope you can see it nicely. If that's the case, that means we need to continue to the next neighbor. Otherwise I can, because it's a 1 now, so I can basically add this to visit. So visit dot add this row, sorry, new row and new column that I can add to my visit. And then also what I can do is I can add this to my big queue. So queue dot append and queue dot append. Yeah, I think that this should work. Yeah, so we can add that like same way we have added it to our visit set. All right. Now, as I think this is exactly what we have written in the pseudocode while we were like going over the concept. And I would rather have you just seen the video until the concept and then write your solution yourself. Seeing the code is basically, the big part of like solving this problem is just like translating your like basically the approach that you're thinking and just into the code, because there are a lot of things that you learn there. Like that's the whole point of like converting your ideas into like the solution. That's how things work when you're like developing a new app. Like you have this idea and then you're writing the code. Well, at this point, like it's ChatGPT and everything, but at least this really like builds up your intuition about like solving problems using the code. Now if we have added anything to my queue, then means I will have to process those into the next minute. I should have named it a time minute, but like this is also pretty good. Okay, so what do I do now? I will return time, but there is a catch. What's the catch? I can only return time if the length of visit is equals to the total number of oranges. If this is equals to total number of oranges, that means I have visited all the oranges. All the oranges have gone bad. We were successful. No orange eating. The return time, else return -1. Okay, before I test it, let's do some typos checks. Yes, that's the typo. Then there might be some other mistake. It's a long code, right? Like so it's easy to make these mistakes while trying to just wrap up this. And then I think there is another thing right here. Yes, I forgot to add that. If you are basically visiting this, adding this to queue already, so that means you're done visiting that rotten orange. So it's better that we add it here to basically my visit. So I'm adding that to my visit. So R, C, that's it. I'm adding it to my visit. All right. And I think yeah, we have to add that. Otherwise we could have done it like we could have added it like right here as well, but like it doesn't matter anyway. And another thing is this has to be out at this level. It's not going to be at the level of 4, because you're visiting oranges at 1 level. You're done visiting those oranges. If I zoom out and just expand this, then it will look exactly like how we wanted it. All right, that's our entire code. Let's run it. Let's run and test it. Okay, add set add is visit.add inc. Yeah, I'm telling you guys, it's just so easy to make these mistakes. And hopefully this time, yes. Okay, let's submit it. And then we can write the time complexity and space complexity. So time complexity, worst case, is going to be big of n into m, or we can say m cross n. That's the total number of cells we are visiting. And space complexity is going to be big of m cross n as well. That's because we are adding them that number of cells. This basically represent the number of cells this grid is going to have, and that it might happen that like when there might be all the oranges are like rotten and we are just appending them again and again and again. Yeah, you're playing again and again and again, but you're looking at your dreams and reviewing it every day, and it's not over until I get it. Whatever. Okay. All right. Marking this solved. See you guys later in the next round. Bye bye.